There's something humbling about standing under a night sky, isn't there? That vast, endless expanse above us, dotted with stars, planets, and galaxies, holds stories older than time itself. But here's the thing, every flicker of light, every shadow in the cosmos, isn't just a distant speck. It's a chapter in the universe's grand narrative, waiting to be unraveled. Today, we're not just stargazing, we're stepping into a cosmic library where each of these 29 celestial tales rewrites what we thought we knew about reality. From the gravitational grip of black holes to the invisible hand of dark matter shaping galaxies, these aren't just facts. They're revelations that challenge our very place in the universe. Think about the last time you looked up and felt small under that infinite sky. Now, imagine peeling back the layers of that darkness to discover it's alive with motion, with drama, with mysteries that defy explanation. That's the journey we're taking together. This isn't just a list of space phenomena. It's a collection of turning points, moments where humanity's understanding of existence was forever altered. Some of these stories are etched in the glow of dying stars, while others hide in the silence between galaxies, whispering secrets we're only beginning to decode. What if I told you the universe is expanding faster than we ever predicted, or that there are places where time itself bends? These aren't plot twists from a sci-fi novel. They're real, documented wonders that scientists are racing to understand. And that's the magic of this exploration. You're not just a spectator. With every revelation, you'll piece together a new fragment of the cosmic puzzle, seeing the night sky not as a static canvas but as a living, breathing entity. So let's begin with the first of these 29 narratives, where the boundaries of space and imagination blur, and the universe starts to tell its story, one astonishing discovery at a time. The story of our universe begins not with a whisper but with a roar, an unimaginable burst of energy and matter erupting from a single point smaller than an atom. This was the Big Bang, the moment when time, space, and everything we know came into being. But here's what's truly mind-bending. We can still see the afterglow of that moment today. It's called the cosmic microwave background radiation, and it's like the universe's very first baby picture, a snapshot taken when everything was just 380,000 years old. Picture this, you're holding a thermal photograph of the night sky, and instead of stars, you're seeing the faint heat signature left over from the birth of the cosmos itself. Scientists discovered this cosmic fingerprint by accident in 1965, when two radio astronomers kept hearing a persistent static no matter where they pointed their antenna. At first, they thought it was pigeon droppings interfering with their equipment. But that static turned out to be the most important noise in history, the cooled down remains of the universe's fiery beginnings. The temperature of that radiation is almost perfectly uniform, just 2.7 degrees above absolute zero, with tiny fluctuations no bigger than 1 part in 100,000. Those microscopic variations are cosmic gold. They show us where matter first started clumping together, eventually forming galaxies and stars. Yet this baby photo holds puzzling contradictions. One of the biggest is called the horizon problem. If you look at opposite sides of the sky, the background radiation is nearly identical in temperature. But those regions were too far apart to have ever been in contact, even in the early universe. It's like finding two identical snowflakes on opposite sides of the planet that somehow formed the same way without ever touching. To solve this, physicists proposed inflation theory, the idea that in the first fraction of a second, the universe expanded faster than the speed of light, stretching quantum fluctuations into the large-scale structures we see today. What's astonishing is that all of this, every star, every planet, every one of us traces back to that single explosive moment. The iron in your blood, the calcium in your bones, even the oxygen you're breathing right now were forged in the hearts of stars that wouldn't exist without those initial ripples in space-time. The Big Bang isn't just our origin story, it's the foundation for every cosmic mystery we're about to explore. And as we peel back its layers, we're not just studying the past, we're uncovering the blueprint for everything that followed. Now imagine a force so powerful it shapes the entire universe, yet so elusive we can't see it, touch it, or even detect it directly. This is the enigma of dark matter, the invisible scaffolding that makes up 85% of all matter in existence. Without it, galaxies would fly apart, cosmic structures wouldn't form, and the night sky as we know it would vanish into chaos. But how do we know it's there if it's completely transparent to light? The answer lies in the cosmic detective story of the Bullet Cluster, one of the most compelling pieces of evidence we have. Picture two galaxies colliding at millions of miles per hour, a violent cosmic crash so immense it warps the fabric of space itself. When astronomers observed this system, they found something startling. The visible matter, stars and gas, piled up in the center of the collision, just as expected. But the gravitational lensing effect, which bends light like a magnifying glass, revealed most of the mass wasn't where the stars were. Instead, it passed right through the collision like a ghost, leaving its gravitational fingerprint far from the visible wreckage. That missing mass, dark matter, here's where things get even stranger. For decades, scientists assumed dark matter must be some kind of undiscovered particle, perhaps a WIMP or weakly interacting massive particle. But after countless experiments deep underground, in particle colliders, and even in space, we've found nothing, not a single definitive trace, which raises a thrilling possibility. What if dark matter isn't a particle at all? Some theories suggest it could be primordial black holes from the early universe. Others propose modifications to gravity itself, that Einstein's equations might need rewriting on cosmic scales. The implications are staggering. If dark matter defies our current understanding of physics, it means the universe operates by rules we haven't even dreamed of yet. Every galaxy, every cluster, every filament in the cosmic web is held together by something we can't explain. And that's the beauty of this mystery. It's not just a gap in our knowledge. It's a doorway to entirely new physics, waiting for the next generation of telescopes, detectors, and brilliant minds to pry it open. So when you look up at the Milky Way's glowing band tonight, remember, what you're seeing is just the glittering surface. The real story is written in the darkness between the stars. If dark matter is the universe's invisible scaffolding, then dark energy is its mysterious engine, pushing the cosmos apart at an ever-increasing speed. While dark matter pulls galaxies together with its gravitational grip, dark energy does the opposite, stretching space-time itself in a cosmic tug of war we're only beginning to understand. The discovery of this force came from one of the most violent events in the universe, the explosive deaths of massive stars called supernova. In the late 1990s, two teams of astronomers made a startling observation while studying distant supernova. These stellar explosions, which should have appeared dimmer the farther away they were, instead shone brighter than expected. The only explanation, the space between galaxies wasn't just expanding, it was accelerating. Imagine blowing up a balloon with dots on its surface, then watching in shock as the dots start moving apart faster and faster without any extra air being added. That's the eerie effect dark energy has on our universe. The discovery was so groundbreaking it earned the researchers the Nobel Prize in Physics in 2011. What makes dark energy even more baffling is that it behaves like the opposite of gravity. While gravity pulls matter together, dark energy seems to be an inherent property of empty space itself, a repulsive force that grows stronger as the universe expands. Some theories suggest it could be Einstein's cosmological constant, a term he famously called his greatest blunder before removing it from his equations. Others propose it might be a dynamic field called quintessence, changing in strength over time. But here's the twist. If dark energy continues to dominate, the universe could face a big rip, where galaxies, stars, and even atoms are torn apart in a far future cataclysm. Yet the biggest question remains, does dark energy mean Einstein's theory of gravity is incomplete? On cosmic scales, his equations might need revision, a possibility that keeps physicists awake at night. Current telescopes like the Dark Energy Survey and upcoming missions like the Euclid Space Telescope are mapping the universe's expansion with unprecedented precision, hunting for clues in the large-scale structure of galaxies. Every measurement brings us closer to understanding whether dark energy is a constant force or something far stranger. One thing's certain, this invisible driver isn't just shaping the universe's fate, it's challenging the very foundations of physics. Right now, as you sit watching this, our entire galaxy is racing through space at over 1 million miles per hour, not just drifting, but pulled by something colossal lurking in the cosmic shadows. This is the Great Attractor, a gravitational mystery so powerful it's dragging the Milky Way and countless other galaxies toward it like moths to a flame. But here's the catch, we can't actually see what's doing the pulling. Our view is blocked by the thick dust and stars of our own galaxy's disk, leaving scientists to piece together clues from the peculiar motions of galaxies around us. Picture the universe as a rushing river with galaxies floating on its surface. While most are carried along by the flow of cosmic expansion, some, like ours, are caught in a hidden current, veering off course. Astronomers first noticed this anomaly in the 1970s when mapping the motions of nearby galaxies. Instead of moving uniformly apart, entire clusters were streaming toward a single point in the sky near the constellation Centaurus. The gravitational force required to explain this movement suggested a mass equivalent to tens of thousands of Milky Ways packed into a region just a few 100 million light-years across. But what could possibly be that massive? Early theories pointed to the Norma cluster, a dense gathering of galaxies in the suspected direction, yet even that couldn't account for the sheer scale of the pull. Then came an even more startling realization. The Great Attractor might just be a waypoint. Beyond it lies something far larger, the Shapley supercluster, a staggering collection of galaxies over 400 times the mass of our local group. It's as if we've been tracking a footprint, only to realize it belongs to a giant standing just beyond the horizon. The plot thickens when you consider how little we still know. Infrared and radio telescopes have peered through the Milky Way's dust, revealing glimpses of galaxy clusters aligning with the attractor's pull. But the true nature of this cosmic magnet remains debated. Could it be a concentration of dark matter so dense it warps spacetime itself? Or is there an even more exotic structure waiting to be discovered? One thing's certain, as our galaxy hurtles toward this unseen Leviathan, it's not just carrying stars and gas, it's carrying us on a collision course with one of the universe's best-kept secrets. Every measurement, every new map of galactic motion, brings us closer to understanding the invisible hand guiding our path through the cosmos. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars, many hosting planets in the so-called Goldilocks zone, where conditions are just right for life. Given those staggering numbers, the math suggests we should be swimming in alien civilizations. So why does the cosmos feel so eerily empty? This is Fermi's paradox, the unsettling gap between what should be and what we actually observe. Physicist Enrico Fermi famously captured this contradiction in a single, cutting question. Where is everybody? One chilling explanation is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar levels. Maybe the filter lies in our past. Perhaps the jump from simple chemistry to self-replicating life is so astronomically unlikely that Earth is a cosmic fluke. Or worse, the filter could still be ahead of us. If most civilizations destroy themselves before achieving spacefaring technology through climate collapse, nuclear war, or unchecked artificial intelligence, then our own future might hold the answer to why the stars are silent. Then there's the zoo hypothesis, the idea that advanced civilizations are deliberately avoiding contact, treating humanity like a protected wildlife reserve. It's not as far-fetched as it sounds. Consider how anthropologists study uncontacted tribes today, observing from a distance to avoid disruption. If alien societies operate under some galactic prime directive, they might be watching us right now, waiting for humanity to reach a certain level of maturity before revealing themselves. But what if the truth is even stranger? Some scientists speculate that advanced life could have transitioned beyond physical forms, uploading consciousness into vast digital realms or manipulating dimensions we can't perceive. Others suggest we're simply too early, that the universe is still young, and we're among its first inhabitants in a cosmic dawn. Or perhaps, as some theories propose, interstellar travel is fundamentally impractical, with physics itself acting as an unbreakable speed limit that traps civilizations around their home stars. The silence isn't just a scientific puzzle, it's a mirror. Every time we scan the skies and hear nothing, we're forced to confront our own assumptions about intelligence, progress, and survival. Are we the lucky ones who slipped past the Great Filter, or are we hurtling toward it unseen? The answer might not lie in distant star systems, but in the choices we make here on Earth. One thing's certain, the longer the silence persists, the louder the question becomes. One summer night in 1977, a radio telescope in Ohio picked up something that defied all expectations. A narrowband signal so intense, so perfectly tuned to the frequency of interstellar hydrogen, that the astronomer who discovered it scrawled, "Wow." In red ink across the printout, that single word became the name of one of the most tantalizing mysteries in the search for extraterrestrial intelligence. For 72 seconds, the Big Ear telescope at Ohio State University recorded a pulse 30 times stronger than the background noise of space, coming from the direction of the constellation Sagittarius. Then, just as suddenly as it appeared, it vanished, never to be heard again. What made this signal extraordinary wasn't just its strength. It matched the exact frequency that scientists had predicted an alien civilization might use to announce its presence, 1420 megahertz, the natural emission line of hydrogen, the most abundant element in the universe. Think of it like tuning a radio to the cosmic equivalent of Middle C, a universal channel any advanced species would recognize. The signal also displayed a telltale Doppler shift, as if it were coming from a distant source moving through space. But here's the twist. Despite decades of follow-up observations, including searches by modern telescopes like the SETI Institute's Allen Telescope Array, nothing like it has ever been detected since. Skeptics have proposed natural explanations, perhaps a passing comet reflecting radio waves or an undiscovered astrophysical phenomenon. But comets don't emit narrowband signals, and no known celestial object matches the WOW signal's unique profile. Even more intriguing is its duration. 72 seconds is exactly how long the Big Ear telescope's fixed antenna would have observed a stationary point in the sky as Earth rotated. If the signal was artificial, it either stopped transmitting the moment the telescope moved away, or more chillingly, someone or something deliberately timed it to match the telescope's window of detection. The mystery deepens when you consider the signal's origin point. Sagittarius isn't just any direction, it's where the center of our galaxy lies, a region dense with stars and potential planetary systems. If an intelligent source sent that signal, they'd need a transmitter vastly more powerful than anything we've built, suggesting technology far beyond our own. Or perhaps it wasn't a deliberate message at all, but a fleeting accident, a cosmic radar blip, or an errant broadcast from a civilization that's long since vanished. What lingers isn't just the question of what caused the wow signal, but what it represents. In a universe where silence overwhelmingly dominates, that one brief burst stands as a tantalizing outlier, a single note in an otherwise empty symphony. Whether it was a natural anomaly or the closest we've ever come to hearing an alien voice, it reminds us that the cosmos still holds surprises we can't yet explain. And that's the thrill of the hunt. Sometimes the most profound discoveries aren't the answers we find, but the questions they leave echoing in the dark. Imagine watching a streetlight flicker unpredictably, sometimes dimming just a little, other times plunging into near darkness for days. Now picture that streetlight is a star over 1,000 light-years away, and its strange behavior has astronomers debating everything from cosmic catastrophes to alien engineering. This is Tabby's star, officially known as KIC 8462852, a celestial mystery that's rewritten how we study the universe, not just with telescopes, but with the collective curiosity of millions. The story begins in 2015, when citizen scientists sifting through data from NASA's Kepler spacecraft flagged something bizarre. Most planet-hunting stars show regular, slight dips in brightness as orbiting worlds pass in front of them. But Tabby's star didn't play by the rules. Its light dropped by up to 22% in uneven, jagged patterns, like someone was slowly drawing a cosmic curtain across it. Even stranger, historical records showed the star had been fading overall for over a century. Astronomers scrambled to explain it. Could it be a swarm of comets so vast it blocked a significant portion of the star's light? Or maybe a colossal collision between planets, leaving behind a cloud of debris. Then came the most provocative theory: megastructures. Physicist Freeman Dyson once hypothesized that advanced civilizations might build vast energy-collecting arrays around stars, structures we now call Dyson spheres. Tabby's star's irregular dimming seemed to fit no natural model perfectly, leading some to wonder if we were glimpsing something artificial. The idea ignited media frenzy, but it also sparked something deeper, a realization that solving cosmic puzzles isn't just for professionals. When the star's next dimming event was predicted, astronomers didn't have enough telescope time to monitor it continuously, so they turned to the public. Thousands of backyard astronomers and amateur stargazers joined the effort, tracking the star's brightness nightly. Crowdfunding campaigns raised over $100,000 for professional observatory time. The collaboration paid off. Detailed observations revealed the dimming was wavelength dependent, meaning some colors of light were blocked more than others. That pointed to fine dust, not solid megastructures, as the likely culprit, but the dust itself is still a mystery. Why is there so much of it, and what's causing the century-long fading? Tabby's star taught us two profound lessons. First, the universe still holds phenomena that defy textbook explanations, keeping even the brightest minds humbled. Second, the search for answers isn't confined to ivory towers. It's a shared human endeavor. Every time a curious person checks a star chart or backs a science project, they're part of the same story that began when humanity first looked up and wondered. The cosmos doesn't give up its secrets easily, but with enough eyes on the sky, even the strangest enigmas start to make sense. When NASA's twin Pioneer spacecraft drifted beyond the orbits of Neptune and Pluto, they carried more than just instruments. They carried humanity's curiosity into the depths of interstellar space. But as these intrepid probes journeyed farther from the Sun, something bizarre happened. They began slowing down ever so slightly, as if an invisible hand were tugging them backward. This tiny deviation, just a fraction of a nanometer per second squared, became known as the Pioneer Anomaly, a cosmic puzzle that would haunt physicists for decades. At first, scientists assumed it was a simple glitch, perhaps thrust from leaking fuel or heat radiating unevenly off the spacecraft. But as they painstakingly reconstructed every possible variable, the anomaly refused to vanish. The deceleration was too consistent, too persistent, matching neither known physics nor any onboard system error. It was as if the probes were sailing against a faint cosmic current, one that didn't appear in any textbook. The implications were staggering. Could there be an unseen gravitational pull from undiscovered matter in the outer solar system? Or was this a whisper of new physics, a flaw in Einstein's theory of gravity that only revealed itself in the icy void between stars? The mystery deepened when researchers realized other distant spacecraft like the Galileo and Ulysses missions showed similar, though less precise, deviations. Yet Voyager, humanity's farthest-flung probes, didn't exhibit the effect at all. This inconsistency only fueled the debate. Some theorists proposed exotic explanations, like the influence of higher dimensions or a subtle drag from dark matter. Others pointed to more mundane but elusive causes, like the way heat from the probe's plutonium power sources might have nudged them off course over time. Then, in 2012, a team of scientists made a breakthrough. By reconstructing Pioneer's heat emissions down to the watt, they found the answer hiding in plain sight: thermal radiation. As the probe's radioactive generators decayed, heat radiated asymmetrically off their dish-shaped antennae, creating just enough recoil to account for the anomaly. The case seemed closed until skeptics noted that the math still didn't perfectly align. While most of the anomaly vanished under this explanation, a faint discrepancy lingered, leaving room for those who still wonder if something deeper is at play. The Pioneer Anomaly is more than a technical footnote. It's a reminder that even our most precise machines can become cosmic Rosetta Stones, revealing hidden truths about the universe. Whether the final answer lies in thermal physics or uncharted gravitational laws, one lesson endures: when humanity sends probes into the unknown, they don't just explore space, they test the boundaries of our understanding. And sometimes the smallest deviations point to the biggest questions. In October 2017, astronomers spotted something unprecedented: a visitor from another star system hurtling through our solar system at nearly 200,000 miles per hour. Named Oumuamua, Hawaiian for scout, this interstellar traveler wasn't just remarkable for its origin. Its bizarre behavior would ignite one of the most heated debates in modern astronomy. At first glance, it appeared to be a simple asteroid, a dark, reddish rock tumbling through space. But when scientists tracked its trajectory, they noticed something impossible to ignore: it was speeding up. This wasn't just ordinary acceleration from gravity. Oumuamua was gaining velocity as it moved away from the Sun, as if pushed by some unseen force. Comets often exhibit similar behavior when their ices vaporize in sunlight, creating a faint thrust. Yet Oumuamua showed no signs of outgassing, no telltale coma or tail of dust and gas. So what was propelling it? One theory suggested it might be a hydrogen iceberg, a fragile chunk of frozen hydrogen slowly evaporating in sunlight, leaving no visible trace. Others proposed it could be a cosmic dust bunny, an ultra-light aggregate of particles barely held together by gravity. Then came the most controversial idea. What if Oumuamua wasn't natural at all? Harvard astrophysicist Avi Loeb famously speculated that its unusual shape potentially elongated like a cigar, and sudden acceleration matched predictions for an artificial light sail, a technology humanity is already developing for interstellar probes. The notion sparked fierce backlash, with critics arguing that extraordinary claims require extraordinary evidence. Yet the mystery only deepened when researchers realized Oumuamua's brightness varied dramatically as it tumbled, suggesting an irregular, possibly flat shape unlike any known asteroid. By the time telescopes could turn toward it, Oumuamua was already too distant to study in detail, leaving scientists with a frustratingly incomplete dataset. Was it a fragment of a shattered exoplanet, a rare type of comet with invisible outgassing, or something even more exotic? The truth is, we may never know. But Oumuamua's fleeting visit did something profound. It shattered our assumptions about interstellar objects. Once thought to be rare, we've since discovered more, like the comet Borisov in 2019. Each new visitor forces us to reconsider what's out there, lurking in the vast dark between stars. What makes Oumuamua so captivating isn't just the unanswered questions, it's the realization that our solar system isn't an isolated island. We're part of a dynamic cosmic highway where objects from distant stars pass through like ships in the night. The next time one arrives, we'll be ready. New telescopes like the Vera Rubin Observatory will scan the skies continuously, ensuring we never miss another interstellar messenger. Because if there's one lesson Oumuamua taught us, it's that the universe is far stranger and far more inventive than we ever imagined. Stephen Hawking once made a startling claim that shook the foundations of physics. Black holes, those cosmic vacuum cleaners, might be erasing information from the universe forever. This wasn't just a quirk of gravity, it was a direct challenge to one of quantum mechanics' core principles, that information can never truly be destroyed. Imagine burning a book. The pages turn to ash, but in theory, if you could track every particle of smoke and ember, you could reconstruct every word. But Hawking's calculations suggested black holes break this rule. When matter falls in, it's not just crushed, it's obliterated beyond recovery, leaving no quantum breadcrumbs behind. The implications were staggering. If black holes really do delete information, then the universe has a memory problem. Quantum physics insists that the past influences the present in predictable ways, a principle called unitarity. Without it, the entire framework of particles and forces collapses into chaos. For decades, physicists wrestled with this paradox, splitting into two camps. Those who believed Hawking was wrong and information must escape somehow, and those who accepted that our understanding of reality might need rewriting. Then came a revolutionary idea. What if the information isn't lost at all, but smeared across the black hole's event horizon like a cosmic hologram? This is the essence of the holographic principle, which suggests that all the data swallowed by a black hole is encoded on its two-dimensional surface, like a DVD storing a three-dimensional movie. When the black hole eventually evaporates through Hawking radiation, a slow leak of energy predicted by quantum theory, that information could be subtly imprinted in the escaping particles. It's as if the universe keeps backup files in the most unexpected places, but there's a catch. If information does escape, it might require a violent mechanism, a firewall of ultra-high-energy particles just inside the event horizon, incinerating anything that crosses. This idea, proposed in 2012, was equally troubling. After all, Einstein's general relativity predicts that falling into a black hole should feel uneventful at first, a concept called no drama. Firewalls would turn the event horizon into a lethal boundary, violating relativity's predictions. Suddenly, the paradox wasn't just about information. It was a full-blown clash between quantum mechanics and gravity, two pillars of physics that refused to reconcile. Today, the debate rages on. Some theorists argue for soft hair, subtle quantum imprints on a black hole's surface that preserve information without firewalls. Others explore exotic ideas like wormholes linking the interior to distant points in spacetime. What makes this puzzle so compelling isn't just the theoretical stake, it's the way it forces us to rethink the nature of reality itself. Are black holes cosmic shredders or the ultimate storage devices? The answer might not just solve a paradox, it could reveal the universe's deepest operating system, hidden in the last place we'd think to look. Most of the universe is a bustling metropolis of galaxies, clustered together in vast webs of light and matter. But in the constellation Boötes, there's a place where the cosmic cityscape gives way to a desert, an unimaginably vast emptiness spanning 330 million light-years. This is the Boötes Void, a spherical region so devoid of galaxies it's earned the nickname, the Great Nothing. If you were to place the Milky Way at its center, you'd need to travel tens of millions of years just to reach the nearest neighbor. The question isn't just why this void exists, it's why it defies everything we thought we knew about how the universe arranges itself. When astronomer Robert Kirshner first discovered the void in 1981, the findings seemed almost too extreme to believe. Standard cosmology predicts that matter should clump together in a honeycomb-like structure with filaments of galaxies surrounding smaller voids. But the Boötes Void isn't just a gap, it's a chasm. Imagine punching a hole in a sheet of bubble wrap so large that you'd expect to find hundreds of bubbles inside, but instead, there are only a handful. That's the scale of the anomaly. Current estimates suggest the void contains just 60 galaxies, a fraction of the thousands that should be there based on statistical models. So what could carve out such a barren region? One theory points to an ancient collision between our universe and another bubble universe in the multiverse, a cosmic accident that swept matter away like a plow clearing snow. Others suggest the void might be the imprint of a supermassive black hole from a previous cosmic cycle, a relic of a time before the Big Bang, the wildest hypothesis. That an ultra-advanced civilization has harnessed the energy of entire galaxies, leaving behind a dark metropolis we're only now stumbling upon. Yet the most plausible explanation might be even stranger. Recent simulations show that voids like Boötes could form naturally, through a rare but possible alignment of quantum fluctuations in the early universe. These fluctuations, magnified by inflation, might have created pockets where matter was spread unusually thin. If true, the Boötes Void isn't a flaw in our models. It's a stress test, showing us just how extreme cosmic randomness can get. What makes this emptiness so compelling isn't just its size or rarity. It's the way it forces us to confront the limits of our cosmic maps. When we look at the night sky, we assume the lights are evenly distributed. But the Boötes Void whispers a different story, one where the universe might be far lumpier, far stranger than we ever dared to predict. And that's the thrill of exploration. Sometimes the most profound discoveries aren't found in the glow of stars, but in the darkness between them. Deep in the constellation Serpens, some 4,000 light-years from Earth, orbits a world that would make even the most extravagant jewelers gasp. PSR J1719-1438b isn't just another exoplanet, it's a cosmic chandelier, a sphere so dense and carbon-rich that scientists believe its core has crystallized into a diamond larger than Earth itself. But this isn't the kind of gemstone you'd find in a museum. Born from the ashes of a dead star's catastrophic collapse, This planet is a testament to the universe's alchemy, where unfathomable pressure and heat transform ordinary elements into celestial treasures. The story begins with the planet's host, a pulsar, a rapidly spinning neutron star so dense that a teaspoon of its material would weigh billions of tons. When astronomers detected subtle wobbles in the pulsar's radio signals in 2011, they knew something was tugging on it. What they found was a companion so unusual it defied classification. Roughly 5 times the mass of Earth but only half its width, this ultra-dense world orbits its stellar corpse every 2 hours and 10 minutes. At that distance, temperatures soar to thousands of degrees, and gravitational forces stretch matter into forms we'd never see in our solar system. Here's where the chemistry gets spectacular. The planet's composition points to a former white dwarf star, stripped of its outer layers until only its crystalline core remained. Under pressures millions of times greater than Earth's atmosphere, carbon atoms align into a rigid lattice, the very definition of diamond. But the real marvel isn't just the gemstone beneath the surface. Theoretical models suggest that in the upper atmosphere, carbon could condense into diamond rain, falling through layers of liquid metallic hydrogen like glitter in a snow globe. Picture a world where storms don't bring water, but a hail of microscopic diamonds, glittering as they descend into the planet's crushing depths. Yet for all its allure, this diamond planet is no paradise. The pulsar bombards it with lethal radiation, and tidal forces have likely locked one hemisphere in perpetual scorching daylight, while the other freezes in eternal darkness. Even if we could mine it, a feat requiring technology far beyond our reach, the diamonds themselves would be unlike anything on Earth. Compressed into exotic forms like lonstellate, they'd be harder than any known mineral, possibly reshaping entire industries if we could ever harness them. What makes PSRJ 1719-1438b more than just a cosmic curiosity is what it reveals about planetary diversity. For centuries, we assumed other solar systems would resemble our own. But this diamond world, alongside lava planets and water worlds, proves the universe has a far richer imagination. Every time we discover an outlier like this, we're reminded that the cosmos doesn't just follow rules, it rewrites them, crafting wonders that challenge our very definition of a planet. And somewhere in that glittering darkness, a diamond the size of a star waits, whispering secrets about the violent beauty of creation. Andromeda, our closest galactic neighbor, isn't just a pretty spiral of stars, it's a cosmic predator. For billions of years, this colossal galaxy has been devouring smaller ones, growing larger and more dominant with each celestial feast. Evidence of its violent past lingers in vast streams of stars, like cosmic crumbs scattered across space, tracing the paths of galaxies it has torn apart and absorbed. These stellar trails, discovered by astronomers in the early 2000s, are the smoking gun of Andromeda's galactic cannibalism, revealing a history far more dramatic than its serene appearance suggests. One of its most famous victims was a dwarf galaxy called M32. Today, all that remains is a dense, compact core orbiting Andromeda like a ghost, a grim reminder of what happens when a smaller galaxy strays too close to a gravitational giant. Scientists believe M32 once had sprawling spiral arms, but Andromeda's immense tidal forces shredded them, leaving behind only its heart, a relic now drifting in silent testimony to the violence of cosmic evolution. Even more staggering is the realization that Andromeda isn't done yet. Right now, it's in the process of consuming another galaxy, M33, pulling it apart thread by thread in a slow-motion demolition that will take millions of years to complete. But the most dramatic chapter in Andromeda's story is yet to come. 4 billion years from now, it will collide with our own Milky Way in one of the universe's most spectacular mergers. Imagine two immense spirals, each containing hundreds of billions of stars, drawn together by gravity in an inexorable dance. As they approach, their mutual pull will warp their shapes, stretching their arms into long, luminous ribbons. Then, over hundreds of millions of years, they'll pass through each other, not in a fiery crash as you might expect, but in a slow, graceful intertwining. Stars are so far apart that direct collisions are rare. The aftermath will be breathtaking. The two galaxies will eventually settle into a single, massive elliptical galaxy, their combined stars redistributed into a glowing sphere. New generations of stars will ignite from the compressed gas of the collision, while supermassive black holes at their cores will spiral toward each other, merging in a burst of gravitational waves. Earth, if it still exists, will witness a night sky transformed, no longer a band of Milky Way light, but a dazzling, star-studded orb dominating the heavens. What makes Andromeda's story so compelling isn't just the scale of destruction, but the inevitability of rebirth. Galactic collisions aren't endings, they're catalysts for new beginnings, forging fresh structures from the wreckage of the old. Every time we gaze at Andromeda's faint smudge in the night sky, we're looking at our own future, a reminder that even in the vast, seemingly unchanging cosmos, change is the only constant. At the edge of observable time, where the universe was barely more than a cosmic toddler, sits an impossible monster, Euler's J1342 plus 0928. This ancient quasar, blazing with the light of 1 trillion suns, shouldn't exist, not just because it's distant, but because at only 690 million years after the Big Bang, it hosts a supermassive black hole weighing in at 800 million times the mass of our Sun. That's like finding a skyscraper in the middle of the Stone Age, a structure so colossal, so sophisticated, it defies every model we have for how cosmic giants grow. Quasars are the universe's most violent engines, powered by supermassive black holes devouring matter at staggering rates. But Euler's J1342 isn't just bright, its very existence shatters assumptions. Conventional theories suggest black holes grow slowly, feeding on gas and merging with others over billions of years. Yet here's one that reached nearly 1 billion solar masses before the universe was even 5% of its current age. It's as if nature cheated, skipping the tedious middle steps and jumping straight to the finale. So how did this cosmic overachiever form so quickly? One radical idea points to direct collapse black holes, primordial behemoths born not from stars, but from the instantaneous collapse of vast gas clouds in the early universe. These wouldn't start small, they'd emerge already massive, like cosmic lottery winners born with fortunes. Another theory suggests hyper-efficient feeding, where early black holes gorged on dense, cold gas streams that no longer exist today. Picture a baby whale growing to full size in months by swimming through an ocean of krill. But the most mind-bending possibility, that supermassive black holes didn't form after the first stars, they predated them. In this scenario, pockets of dark matter or exotic physics allowed black holes to seed before starlight even flickered on, rewriting the cosmic timeline entirely. Supporting this, some simulations now show that under the right conditions, black holes could have grown at breakneck speeds in the universe's chaotic infancy, where matter was packed tighter and competition for resources was fierce. What makes Euler's J1342 more than just an outlier is what it implies about our cosmic origins. If black holes this big existed so early, they weren't just passive observers. They were architects, shaping the galaxies around them with furious radiation and gravitational might. Their growth may have catalyzed star formation or, conversely, snuffed it out in vast regions, leaving behind cosmic deserts. Every new discovery like this forces us to reconsider not just how black holes evolve, but how the universe itself transitioned from darkness to light. As telescopes like the James Webb Space Telescope peer even further back in time, the question isn't whether we'll find more of these impossible quasars, it's how many. Each one is a time capsule from an era we're only beginning to understand, a clue written in the fiery script of accretion disks and event horizons, and perhaps hidden in their impossible brilliance lies the answer to one of cosmology's greatest puzzles: how the universe built its giants before the rules were even fully written. If you could step outside the universe and see it from a distance, the view would be breathtaking, not a random scattering of galaxies, but a delicate, luminous tapestry stretching across billions of light years. This is the cosmic web, the grand architecture of existence itself, where galaxies cluster like glittering beads on invisible strings. Those threads, dark matter filaments, form the skeleton of the universe, guiding galaxies into position through their immense gravitational pull. But what's truly uncanny isn't just the web's scale, it's how eerily it mirrors another intricate network, the human brain. Zoom in on a single neuron, with its branching dendrites reaching out to communicate with others, and you'll see a pattern chillingly similar to the universe's dark matter highways. Scientists have even quantified this resemblance. When researchers compared a simulation of the cosmic web to a slice of brain tissue under a microscope, they found the distribution of matter and synapses followed nearly identical mathematical rules. Both systems organize around nodes, galaxies in one, neurons in the other, connected by delicate filaments that channel energy and information. It's as if nature has a favorite blueprint, reused from the microscopic to the cosmic. But how could two things so vastly different in scale share such striking similarities? One explanation lies in the universal laws governing growth. Just as gravity pulls matter into dense clusters along dark matter's invisible scaffolding, electrical signals in the brain strengthen certain neural pathways while pruning others, creating efficient networks. Both systems optimize for the same thing: connectivity. In the brain, it's about processing information quickly. In the universe, it's about matter flowing along the paths of least resistance. The cosmic web wasn't always visible to us. For decades, astronomers mapped galaxies in patches, like explorers charting islands without knowing they were part of a continent. Then, in the early 2000s, large-scale surveys like the Sloan Digital Sky Survey revealed the full picture: galaxies aligned along vast filaments, with yawning voids between them. Supercomputer simulations showed how dark matter, invisible yet dominant, sculpted this structure in the aftermath of the Big Bang, guiding ordinary matter into the luminous patterns we see today. What makes this resemblance more than just a curious coincidence is what it suggests about the hidden patterns of reality. Whether it's the branching veins of a leaf, the tributaries of a river delta, or the distribution of galaxies, certain shapes recur because they're the most efficient solutions to universal problems. The cosmic web isn't just a pretty structure, it's a testament to the deep, underlying order that governs everything from the smallest cells to the largest superclusters. And every time we uncover another thread in this tapestry, we're reminded that the universe may not just be stranger than we imagine, but more familiar too. The moon hangs in our sky as a silent, airless world, barren, unchanging, or so we once thought. But hidden in its ancient rocks lies a startling secret. Our lunar companion once crackled with a magnetic field as strong as Earth's, a protective shield against the solar wind's relentless barrage. Today, that field is gone, leaving behind only ghostly traces in moon samples brought home by Apollo astronauts. How could a world so small, with no atmosphere or flowing water, have ever generated such a force? The answer rewrites everything we thought we knew about our nearest cosmic neighbor. When scientists first analyzed lunar rocks in the 1970s, they expected to find minerals untouched by magnetic fields. Instead, they discovered something impossible: tiny metallic grains permanently magnetized, as if frozen in time under the influence of a powerful field. Further studies pinned this field's strength to roughly 100 microteslas, nearly twice as strong as Earth's is today. For a world just 1% of Earth's mass, this was like finding a hummingbird capable of lifting a car. The implications were staggering. The moon wasn't always the quiet, geologically dead place we see now. Billions of years ago, it may have thrummed with internal energy, its core churning with molten metal like a miniature version of our own planet's dynamo. But how? One leading theory points to a colossal impact early in the moon's history. When a Mars-sized body collided with a young Earth, the debris that coalesced into the moon might have been seeded with superheated, molten material. As this lunar core cooled and crystallized, convection currents, swirling motions of liquid metal, could have generated a temporary magnetic dynamo, much like Earth's does today. Simulations suggest this dynamo might have lasted for over 1 billion years before the moon's small size doomed it. With less internal heat to sustain convection, the core gradually stiffened, and the magnetic field flickered out like a dying light bulb. There's a wilder possibility, though. Some researchers argue that massive asteroid strikes during the moon's volcanic heyday could have temporarily jump-started a magnetic field. Imagine a moon covered in lava oceans, its surface still soft from formation. When a city-sized asteroid slammed into it, the impact could have sent shockwaves through the molten interior, stirring the core like a spoon in a coffee cup. This violent stirring might have created short-lived magnetic bursts, imprinting rocks with magnetization without the need for a long-lived dynamo. It's a cosmic version of striking a bell, brief, resonant, and fading into silence. The mystery deepens when you consider what else was happening at the time. The moon's magnetic field peaked around 3.5 billion years ago, just as volcanic eruptions were flooding its surface with dark plains we now call Maria. Did the same internal heat driving those eruptions also power the dynamo, or was the magnetism a side effect of some even stranger process, like tidal forces from a much closer Earth stretching and heating the moon's interior? Every Apollo sample, every lunar orbiter's measurement adds another piece to the puzzle. But the full picture remains tantalizingly out of reach. What makes this discovery so profound isn't just the science, it's the way it forces us to see the moon anew. No longer just a lifeless rock, it was once a dynamic world with a molten heart, its invisible magnetic embrace shielding its surface from the worst of the young sun's fury. And if something as seemingly inert as the moon could hide such surprises, what other secrets might the solar system's quiet corners hold? The next time you gaze up at its cratered face, remember, those gray plains once rippled with forces we're only beginning to understand, a reminder that even the familiar can be extraordinary when seen through the lens of time. Somewhere in the cosmic deep, a monster is on the loose, a supermassive black hole, weighing as much as 20 million suns, hurtling through intergalactic space at 4.5 million miles per hour. This isn't science fiction. Astronomers first spotted this cosmic fugitive in 2017 as a brilliant streak of light, its path tracing a violent exit from a distant galaxy. But how does something with the gravitational pull of an entire star system get kicked out of its home? The answer lies in the most extreme physics the universe has to offer. The leading theory points to a cataclysmic dance between 3 black holes. Picture 2 galaxies merging, their central black holes spiraling toward each other until they collide, sending ripples through space-time gravitational waves. Normally, such a merger would leave one larger black hole sitting quietly at the center of the new galaxy. but introduce a third black hole into the mix and chaos unfolds. As the original pair merges, the energy released isn't perfectly symmetrical. The newly formed black hole gets a kick in one direction, like a rifle's recoil, except this recoil is strong enough to fling it clear out of the galaxy. Here's where it gets even wilder. The runaway black hole isn't traveling alone. Telescopes revealed a luminous trail of young stars stretching back to its origin, stars that shouldn't exist in the emptiness between galaxies. The explanation: as the black hole plows through intergalactic gas, it compresses and heats the material in its wake, triggering star formation in its turbulent path. It's like a cosmic plow tilling the void and leaving behind a glittering furrow of newborn suns. Not everyone is convinced, though. Some researchers argue the streak of light might be a jet from an active black hole, angled in just the right way to look like motion. Others suggest the black hole could have been ejected by a slingshot effect during a galactic collision, where gravitational interactions between multiple massive objects sent one careening away. What's undeniable is the sheer energy required to dislodge something this massive, equivalent to 100 million supernovas exploding in perfect unison. This discovery forces us to rethink how black holes shape their surroundings. We've long assumed supermassive black holes sit anchored at galactic centers, but now we know some are cosmic nomads wandering the darkness between galaxies. Their journeys might even seed star formation in the most unlikely places, scattering pockets of light across the void. Every time we find an outlier like this, it's a reminder that the universe doesn't just follow the rules, it bends them, breaks them, and sometimes flings them into the abyss at unimaginable speeds. The universe is expanding, that much we know for certain, but when it comes to how fast that expansion is happening, the cosmos seems to be giving us two different answers. This is the Hubble Tension, a stubborn discrepancy that's rattling the foundations of modern cosmology. On one side, we have meticulous measurements of the cosmic microwave background, the afterglow of the Big Bang, which suggest a precise expansion rate. On the other, observations of nearby stars and supernova tell a different story, one where the universe is ballooning faster than those ancient light echoes predict. The difference might sound small, just a few kilometers per second per megaparsec, but in the high-stakes world of precision astronomy, it's a glaring inconsistency that refuses to vanish no matter how many times we check the math. So where does the tension come from? Imagine trying to measure the speed of a car with two different radar guns. One uses the car's engine noise to estimate its velocity, while another tracks its movement directly. If they disagree, either one instrument is miscalibrated or there's something strange about the car itself. In cosmology, the engine noise is the cosmic microwave background, analyzed by missions like Planck to infer the expansion rate indirectly through the universe's early physics. The direct tracking comes from observing pulsating stars called Cepheids and cataclysmic supernova in nearby galaxies, which act as cosmic speedometers. The problem: these methods keep disagreeing, and the gap widens with each new study. Some scientists argue the tension stems from overlooked errors, perhaps dust interfering with supernova measurements, or subtle miscalibrations in the distance ladder used to gauge nearby galaxies. But others suspect something far more exciting, that we're brushing up against undiscovered physics. One tantalizing possibility involves dark energy evolving over time, growing stronger or stranger than our models predict. Another theory introduces early dark energy, a fleeting force that briefly turbocharged the universe's expansion in its infancy, leaving traces we haven't fully accounted for. Then there's the radical notion that dark matter interacts with itself in ways we haven't imagined, subtly warping cosmic structures and throwing off our measurements. The stakes couldn't be higher. If the Hubble tension isn't just a measurement glitch, it means our standard model of cosmology, the meticulously crafted playbook explaining everything from galaxy formation to the universe's fate, is missing a crucial chapter. Future telescopes like the Roman Space Telescope and the Vera Rubin Observatory aim to settle the debate with even sharper data. But for now, the tension remains, a crack in the cosmic facade that might just be wide enough to glimpse an entirely new physics lurking behind it. Whether it's a flaw in our tools or a flaw in our theories, one thing's certain: the universe is holding something back, and the answer could rewrite the story of everything. Galaxies should follow certain cosmic rules, spiraling arms held together by dark matter's invisible grip, stars orbiting in predictable patterns dictated by gravity. But then there's NGC 1277, a relic from the early universe that refuses to play by those rules. This massive galaxy, nearly as wide as the Milky Way but compressed into a dense disk, spins too fast for its own good. According to our models, it should fly apart, its stars scattering into the void like marbles spilled from a bag. Yet somehow, it holds itself together without the dark matter scaffolding every other galaxy seems to need. It's as if we've found a skyscraper standing tall with no foundation, defying the laws of physics as we know them. The discovery sent shockwaves through astronomy when it was confirmed in 2018. Normally, galaxies are embedded in vast halos of dark matter, which outweighs visible stars and gas by a factor of 10 to 1. But measurements of NGC 1277's motion revealed something startling. Its stars alone accounted for nearly all its mass. Where dark matter should have been, there was only silence. At first, scientists suspected an error. Perhaps the observations missed faint stars or hidden gas. But follow-up studies with the Hubble Space Telescope only deepened the mystery. This galaxy wasn't just lacking dark matter, it was thriving without it, a cosmic rebel in a universe built on unseen forces. So how does a galaxy like this even form? One theory suggests a violent past. NGC 1277 sits near the center of the Perseus cluster, a crowded neighborhood of galaxies engaged in gravitational tug-of-wars. In this chaos, it might have been stripped of its dark matter halo long ago, torn away by the cluster's collective pull like a thief in the night. Alternatively, it could be a fossil from a time before dark matter dominated, a rare survivor of an era when ordinary matter ruled the cosmos. Some simulations even propose that under the right conditions, galaxies could form in dense, turbulent regions where normal matter clumps together fast enough to bypass dark matter's influence entirely. But NGC 1277 isn't alone. Other oddballs like Dragonfly 44 present the opposite puzzle: galaxies that are almost entirely dark matter, with barely any stars at all. Together, these outliers force us to confront an uncomfortable truth. Our models of galaxy formation might be incomplete. For every rule we've written about how the universe works, there seems to be an exception whispering, "Think again." What makes these impossible galaxies so valuable isn't just their defiance, it's the way they sharpen our questions. Are they statistical flukes or signposts pointing to a deeper complexity in cosmic evolution? Every time we find another one, we're reminded that the universe doesn't owe us simplicity. It's a laboratory of extremes where the rarest specimens often hold the keys to the biggest breakthroughs. And perhaps hidden in the light of these enigmatic islands of stars lies a clue that will rewrite the story of how everything came to be. One moment, space is silent. The next, a torrent of radio waves erupts from the void, packing more energy than the sun emits in 80 years, all in less time than it takes to blink. These are fast radio bursts, or FRB, the universe's most enigmatic signals. First detected in 2007, These fleeting cosmic flashes last mere milliseconds, yet their origins remain one of astronomy's fiercest puzzles. What could possibly unleash such staggering energy so briefly, so unpredictably, and from such incomprehensible distances? The theories range from the catastrophic to the downright alien, each more mind-bending than the last. Take FRB 121102, one of the most famous bursts. Discovered in 2012, it wasn't just powerful, it repeated. Unlike one-off FRBs, this one flickered on and off like a malfunctioning beacon, ruling out explanations involving singular, destructive events like neutron star collisions. Then came FRB 2019-0520, which pinned its location to a spiral galaxy remarkably similar to our own Milky Way, challenging assumptions that FRBs only came from extreme environments. The plot thickened when some burst showed bizarre sub-pulses, as if encoded with hidden structure. It's as if the cosmos is taunting us, offering clues just cryptic enough to keep us guessing. So what's behind these cosmic fireworks? One leading suspect is magnetars, neutron stars with magnetic fields so intense they could strip the data from a credit card halfway across the galaxy. When these stellar corpses undergo starquakes, sudden cracks in their ultra-dense crusts, they might unleash bursts of energy detectable across the universe. Supporting this, in 2020, astronomers caught a magnetar in our own galaxy emitting an FRB-like signal, the first smoking gun linking these objects to the mystery. But not all FRBs fit this mold. Some repeat randomly, others are one-offs, and a few even arrive with lower frequency afterglows, suggesting multiple mechanisms might be at play. Then there's the wild card, extraterrestrial intelligence. While most scientists consider natural explanations far more likely, the peculiar patterns of some FRBs have sparked speculation. Could they be power signatures of alien megastructures, or even deliberate signals amplified by cosmic-scale transmitters? The truth is, we can't yet rule it out, not because it's probable, but because FRBs defy so many expectations. Their very randomness makes them maddeningly hard to study. By the time telescopes swing toward their origin, the burst is already history, leaving behind only a ghostly imprint in the data. What makes FRBs more than just a celestial curiosity is what they reveal about the universe's unseen fabric. As these waves travel billions of light years, they interact with the sparse electrons between galaxies, allowing astronomers to map the cosmos' missing matter. The invisible stuff theories say should exist but telescopes can't see. Each burst is like a flashlight beam in a cosmic fog, illuminating the darkness between galaxies, and with new observatories like the Chime telescope in Canada detecting dozens per month, we're on the verge of a revolution in understanding. The thrill of FRBs isn't just in solving their mystery, it's in the reminder that the universe is still full of surprises. Just when we think we've catalogued its phenomena, something new flickers to life in the static, daring us to listen closer. Whether they're the death cries of collapsing stars, the hum of alien engines, or something stranger still, one thing's certain: every millisecond burst is a message in a bottle, washed ashore from the farthest reaches of space and time. And we're only just learning how to read them. Beyond Neptune's orbit, in the frozen fringes of our solar system, something strange is tugging at the fabric of gravity. A handful of icy objects in the Kuiper belt, the ring of debris left over from the solar system's formation, aren't moving the way they should. Their orbits tilt at odd angles, clustering in ways that defy the pull of the known planets. The best explanation: a hidden giant, a world up to 10 times the mass of Earth, lurking in the darkness so far from the sun that a single year there could last 20,000 of our own. This is the Planet 9 hypothesis, and it's not just a hunch, it's a mathematical scream from the outer solar system, demanding we pay attention. The story starts with Sedna, a dwarf planet discovered in 2003 with an orbit so stretched and tilted it resembled a cosmic eyebrow raised in suspicion. Then came more oddballs, 2433-339, a Kuiper belt object with an orbit perpendicular to the planets, and 2015 BP519, which loops around the Sun backward compared to everything else. Alone, each might be written off as a fluke, but when astronomers tracked their paths, they noticed something chilling. These orbits weren't just random. They pointed in the same direction, as if something massive had herded them like celestial sheep. Enter Caltech astronomers Mike Brown and Konstantin Batygin. In 2016, they crunched the numbers and found the odds of this clustering happening by chance were just 1 in 15,000, the only plausible culprit. A distant, undiscovered planet, its gravity sculpting these orbits over billions of years. Their simulations showed a world roughly 5 to 10 Earth masses, tracing an elliptical path so vast it never ventures closer than 20 billion miles from the Sun, over 7 times farther than Neptune. At that distance, it would reflect so little sunlight that even our best telescopes might miss it, but its influence would be undeniable, warping the trajectories of everything that strays too close. The hunt is now a high-stakes race between telescopes and mathematics. Teams scour archival sky surveys, searching for faint dots that move just slightly between images taken years apart. Others use massive observatories like Subaru in Hawaii, methodically scanning the predicted orbital path for any glimmer of reflected sunlight. The challenge is staggering, finding a single, dim object in an area of sky the size of 15,000 full moons. It's like searching for a lone black marble dropped in the middle of the Pacific Ocean at midnight. Skeptics argue alternative explanations could account for the odd orbits, like the collective gravity of many smaller Kuiper belt objects, or even a primordial black hole the size of a bowling ball. But with each new discovery of another anomalously orbiting ice ball, the case for Planet 9 grows stronger. If it's real, it wouldn't just be another planet, it'd be a time capsule from the solar system's violent youth, perhaps a rogue core ejected from the inner solar system long ago, or a captured orphan from another star. Its very existence would rewrite the story of how our cosmic neighborhood formed. The implications ripple beyond astronomy. A confirmation would be a triumph of prediction, proving that even in the age of space telescopes, the solar system still holds secrets waiting to be teased out by pencil and paper. And if searches come up empty, that's equally thrilling. It would mean we've stumbled upon a gravitational anomaly with no easy explanation, a puzzle demanding entirely new physics. Either way, the outer solar system is whispering. The only question is whether we're listening closely enough to hear it call back. Rising like colossal hourglasses from the Milky Way's core, the Fermi Bubbles stretch 25,000 light-years into space, one above the galactic plane, one below, glowing with the ghostly energy of a cataclysm long past. These gargantuan structures, discovered in 2010 by NASA, a Fermi Gamma-ray space telescope, aren't made of gas or dust, but of ultra-hot plasma, crackling with gamma rays and X-rays. They're the scars of a violent outburst from our galaxy's supermassive black hole, a tantrum so powerful it punched through the Milky Way's dense interstellar medium like a fist through fog. What could unleash such fury? The leading theory points to a feeding frenzy. Around 4 million years ago, Sagittarius, a star, the black hole at our galaxy's heart, may have gorged on a wayward star or a massive gas cloud. As matter spiraled into its maw at near light speed, it didn't just vanish, it triggered a colossal jet of energy, blasting outward along the black hole's spin axis. Imagine a pressure cooker with no release valve until suddenly the lid blows sky high. That jet, packed with charged particles and radiation, carved out the Fermi Bubbles in a cosmic eruption lasting hundreds of thousands of years. But the real surprise isn't just their size, it's what they're teaching us about galactic ecosystems. These bubbles act like echo chambers, trapping high-energy particles that would otherwise escape into intergalactic space. Inside them, electrons race along magnetic field lines at nearly the speed of light, emitting gamma rays when they collide with photons. This creates a shimmering boundary, like the surface of a soap bubble, where the Milky Way's violent past meets the quiet of the present. Even now, the bubbles are expanding, their edges rippling with subtle shocks that reveal the density and turbulence of the galactic halo. Other galaxies boast similar structures. The Perseus cluster, 53 million light-years away, shows vast X-ray cavities carved by its central black hole's eruptions, while the galaxy Cygnus displays radio lobes stretching millions of light-years. These aren't anomalies, they're evidence of a universal cycle. Black holes feast, then belch energy, shaping their surroundings in a feedback loop that regulates star formation. Too much outburst activity and galaxies sterilize themselves, too little, and they drown in gas, unable to birth new stars. The Fermi Bubbles are our front row seat to this cosmic balancing act. What's mesmerizing is how these structures linger. Long after the eruption that created them faded, the bubbles remain, fossilized energy from an era when early humans were just beginning to walk upright. They're a reminder that galaxies aren't static, they breathe, they convulse, they evolve. And somewhere in their glowing depths, written in the language of particle collisions and magnetic fields, lies the next chapter of our understanding. How the most violent forces in existence sculpt the very frameworks that make life possible. On August 17, 2017, the universe sent us a gift, a ripple through space-time and a flash of light that would rewrite astronomy textbooks. For the first time in history, scientists detected both gravitational waves and electromagnetic radiation from the same cataclysmic event. Two neutron stars colliding 130 million light-years away. This wasn't just a breakthrough, it was a cosmic Rosetta Stone, revealing secrets about the universe's most extreme physics and the origins of the very elements that make up our world. The story begins with LIGO and Virgo, gravitational wave observatories that had already made headlines by detecting black hole mergers. But this signal was different. Instead of the abrupt chirp of colliding black holes, the detectors picked up a sustained vibration lasting nearly 100 seconds, the telltale spiral of two ultra-dense stellar corpses locked in a death dance. Seconds later, NASA Fermi satellite caught a gamma ray burst from the same patch of sky, setting off a frantic global hunt. Telescopes across the planet swiveled toward the constellation Hydra, racing to capture the aftermath of what would become known as GW 170817. What they witnessed was nothing short of cosmic alchemy. Neutron stars, the crushed cores of dead suns, are so dense that a sugar cube-sized piece would weigh as much as Mount Everest. When these two monsters collided, their impact forged elements heavier than iron in a process called rapid neutron capture, or the R process. For decades, scientists had theorized that events like this were the universe's primary goldsmiths, but until that night, it was just an elegant guess. Then, as the kilonova's glow spread across the spectrum from blue to red, spectroscopy revealed the unmistakable fingerprints of gold, platinum, and other precious metals, proof that the rings on our fingers and the chips in our phones were born in explosions like this. The data held even more surprises. The collision ejected a jet of material moving at nearly the speed of light, which later produced X-ray and radio emissions detectable for weeks. By combining gravitational wave measurements with traditional astronomy, researchers pinned down the Hubble constant, the universe's expansion rate, with unprecedented precision. It was like hearing an explosion and seeing the flash simultaneously, allowing scientists to triangulate cosmic distances in an entirely new way. But perhaps the most profound revelation was how much we still don't know. The event produced far more heavy elements than models predicted, suggesting neutron star mergers might be even more efficient cosmic forges than we imagined. Some of the light curves didn't match expectations, hinting at exotic physics in the superdense debris. And the fact that we caught this event so soon after turning on gravitational wave detectors implies these collisions might be astonishingly common, meaning the universe is constantly seeding itself with stardust turned to gold. This single observation bridged two eras of astronomy. It proved that gravitational waves and light aren't just parallel phenomena, they're complementary voices in the same cosmic conversation. Every gold necklace, every uranium atom, even the iodine in our bodies can trace its lineage back to violent unions like this, scattered across space and time. The kilonova of 2017 didn't just illuminate the darkness, it showed us we're made of the very echoes of stellar catastrophes, stitched together across billions of years. And somewhere out there, another pair of neutron stars is spiraling toward collision, waiting to tell us secrets we haven't even thought to ask about yet. Right now, dark energy is the universe's quiet architect, gently pushing galaxies apart in a slow-motion expansion. But what if it wasn't so gentle? What if, instead of a steady nudge, this mysterious force grew stronger over time, accelerating until it didn't just empty the cosmos, it shredded it? This nightmare scenario is called the Big Rip, a hypothetical doomsday where dark energy becomes so dominant that it overpowers every force holding reality together, unraveling the universe atom by atom. The math behind this cosmic apocalypse is as chilling as it is elegant. Dark energy's repulsive force is often modeled by something called the equation of state, a ratio of its pressure to its energy density. If this value dips below -1, dark energy doesn't just persist, it intensifies as space expands. Picture a snowball rolling downhill, but instead of melting, it grows larger and faster with every turn. In this scenario, galaxies would first vanish over the horizon as space stretches faster than light can bridge the gaps. Then, gravity would lose its grip, tearing star systems apart. Planets would drift away from their suns, and eventually, even atoms would be ripped asunder, nuclei torn from electrons in a final, violent instant. The universe wouldn't end with a whimper or a bang, but with a scream of space-time itself. Timelines vary depending on how aggressively dark energy evolves, but some estimates suggest this disintegration could occur in as little as 20 billion years, a blink in cosmic terms. Long before that, the Milky Way would be an island in an ever-darkening void, its neighboring galaxies redshifted into oblivion. The night sky, once glittering with stars, would fade to black as the last photons stretch beyond detectable wavelengths. Even black holes, the universe's most resilient structures, wouldn't survive. Their event horizons would be stretched and split, unleashing their trapped energy in a final, futile burst. Yet for all its drama, the Big Rip remains speculative. Current observations suggest dark energy behaves like a cosmological constant, its strength unchanging over time. But cosmology has a habit of humbling our certainties. What if dark energy isn't constant? Some theories, like phantom energy models, propose it could grow denser as space expands, inching closer to that critical threshold. Others suggest it might interact with dark matter in ways we haven't yet imagined, triggering phase transitions that alter its properties. The mere possibility forces us to confront how little we truly understand about the universe's underlying framework. The Big Rip isn't just a story about how the universe might end. It's a mirror reflecting how precarious existence really is. Everything we know, from the largest galaxy to the smallest DNA strand, relies on a delicate balance of forces. Tweak one variable and the entire cosmic equation collapses. That's the paradox of dark energy. It's the reason we have a universe at all, yet it could also be the architect of its demise. Whether the Big Rip is our fate or just a physicist's thought experiment, it reminds us that the cosmos isn't static. It's a dynamic, evolving arena where even the laws we take for granted might one day rewrite themselves. And in that uncertainty lies both terror and wonder, the thrill of a universe that still keeps its ultimate secrets. What if everything we know, every galaxy, every planet, every choice we've ever made, is just one thread in an infinite tapestry of realities? This isn't science fiction. The multiverse theory, once relegated to the fringes of cosmology, has surged into the mainstream, fueled by cutting-edge physics and the sheer mathematical inevitability that our universe might not be alone. Picture a cosmic foam where each bubble is a self-contained universe with its own laws of physics, its own history, its own version of you reading these words right now. Some bubbles might harbor life, others could be barren wastelands of broken physics, and somewhere out there in the froth of existence, every possible outcome of every quantum decision plays out in parallel. The idea springs from two profound pillars of modern physics. First, eternal inflation, the notion that the Big Bang wasn't a one-time event, but an endless fireworks show of universe-making. In this view, space-time is like a rising loaf of raisin bread, where each raisin is a universe forever drifting apart as the dough expands. Quantum fluctuations in the early cosmos could have sparked countless pocket universes, each with random variations in fundamental constants. Imagine tweaking the strength of gravity or the charge of an electron just slightly. In some bubbles, stars might never ignite. In others, matter might collapse instantly into black holes. Our universe, with its Goldilocks perfect balance, could simply be a lucky draw in a cosmic lottery. Then there's the quantum multiverse, a dizzying offshoot of the many worlds interpretation. Every time a particle faces a choice, to spin left or right, to decay now or later, the universe splits, creating branching timelines where all possibilities unfold. Missed a bus this morning, somewhere, a version of you caught it, decided to move to a different city, another you stayed put. This isn't mere philosophy. Quantum experiments like the double-slit test show particles existing in multiple states until observed, as if reality itself hesitates until forced to choose. If consciousness truly collapses these probabilities, then the multiverse isn't just out there. It's being spun into existence with every thought, every measurement, every breath. Critics argue the multiverse is untestable, a metaphysical cop-out that explains too much by explaining nothing, but evidence might be hiding in plain sight. The cosmic microwave background, that fossilized glow from the Big Bang, could bear scars from collisions with other universes like bruises from a long-ago cosmic bumper car ride. Some researchers claim to have spotted anomalous cold spots in the CMB, potential fingerprints of such an encounter. Others hunt for gravitational echoes or strange distortions in the fabric of spacetime that betray the presence of neighboring bubbles. The implications are staggering. If the multiverse is real, it redefines not just our place in the cosmos, but the very meaning of existence. Are we the protagonists of reality or statistical flukes in an infinite ensemble? Does free will matter if every choice spawns a new universe? And if civilizations rise and fall across countless realities, what does that say about the fate of our own? The multiverse doesn't just expand the boundaries of space, it explodes the boundaries of imagination, leaving us to wonder, in the grand cosmic library of universes, what other stories are written on pages we'll never see. Imagine a snowflake that doesn't just repeat its pattern in space but in time, ticking like a quantum metronome forever without energy or decay. This isn't a thought experiment. It's a time crystal, a phase of matter so bizarre it defies the laws of classical physics. First proposed in 2012 by Nobel laureate Frank Wilczek, these structures don't settle into equilibrium like normal crystals. Instead, their atoms oscillate in a never-ending dance, locked in a loop that repeats predictably without ever winding down. It's as if you spun a top and found it kept spinning on its own, indefinitely, without friction or external force, a perpetual motion machine at the atomic scale. The breakthrough came in 2017 when two separate teams, one at Harvard and another at the University of Maryland, created time crystals in the lab using chains of ytterbium ions and diamond defects. By precisely manipulating these systems with lasers and magnetic fields, they forced the atoms into a rhythm where their spins flipped back and forth like a cosmic pendulum, synchronized yet independent of the energy pulsing through them. The key, these crystals aren't breaking the laws of thermodynamics, they're bending them. While normal systems lose energy to entropy, time crystals exist in a strange quantum limbo, protected from decay by their inherent symmetry. They're not perpetual motion in the traditional sense. They're more like a clock that ticks forever because time itself is part of its structure. But here's where the cosmic implications kick in. If we can engineer time crystals in controlled environments, could they also form naturally in the universe? Neutron stars, the ultra-dense remnants of supernova, might be prime candidates. With magnetic fields trillions of times stronger than Earth's and matter packed so tightly that atomic nuclei are crushed together, these stellar corpses could host exotic quantum states we've barely imagined. Some theorists speculate that the extreme gravitational waves rippling from neutron star collisions might even leave behind transient time crystals, flickering into existence like echoes of the violence that birthed them. The real magic of time crystals lies in their potential applications. Quantum computers, which rely on maintaining fragile superpositions of states, could use time crystals as error-resistant memory, preserving information against the ravages of decoherence. They might even serve as ultra-precise sensors, detecting infinitesimal changes in gravity or magnetic fields with unparalleled accuracy. But beyond practicality, these structures challenge our understanding of time itself. In a universe where entropy dictates the arrow of time, time crystals are islands of order that refuse to fade, hinting at deeper symmetries woven into the fabric of reality. What's thrilling isn't just that time crystals exist, it's that they reveal how much we still don't know about the quantum realm. Every time we think we've mapped the boundaries of physics, nature throws us a curveball, proving the cosmos is richer, weirder, and more inventive than our boldest theories. Whether they are humming silently in the hearts of neutron stars or powering the quantum computers of tomorrow, time crystals are a reminder that the universe's greatest secrets often lie not in the grand and distant, but in the delicate, ticking rhythms of the infinitesimally small. Black holes dominate our cosmic imagination, voracious pits of gravity where matter vanishes forever. But what if the universe has an undo button? Enter white holes, the hypothetical twins of black holes that flip the script entirely. Where black holes pull everything in, white holes violently expel matter and energy, refusing to let anything cross their event horizon. Think of them as cosmic fountains, gushing material back into space instead of swallowing it whole. While no white hole has ever been observed, their existence isn't just science fiction, it's a mathematical inevitability in the equations of general relativity. Einstein's theories allow for them, but the universe seems stubbornly reluctant to build one. So why do physicists take them seriously? Because they might be the missing key to understanding how the universe recycles itself. Picture a black hole's life cycle in reverse. According to some interpretations of quantum gravity, when a black hole dies, slowly evaporating via Hawking radiation, it might not vanish entirely. Instead, it could rebound as a white hole, spewing out all the information and matter it once consumed. This process, sometimes called a quantum bounce, suggests that what we perceive as the end might just be a transformation. It's like compressing a spring to its limit. At some point, it has to snap back. If true, white holes could be the universe's way of balancing the books, ensuring nothing is ever truly lost, just temporarily locked away in a cosmic vault before being returned. The implications ripple across cosmology. If white holes exist, they could explain mysterious phenomena like gamma-ray bursts, those sudden, intense flashes of energy that appear without warning. Some theorists speculate these could be the birth cries of white holes, erupting into existence after a black hole's quantum resurrection. Others propose that the Big Bang itself might have been a white hole event, with all the matter and energy of our universe bursting forth from a singularity. It's a poetic symmetry. If black holes represent the universe's endings, white holes could symbolize its beginnings. Yet for all their theoretical elegance, white holes face a glaring problem. They defy entropy, the universal law that disorder always increases. A white hole's orderly expulsion of energy seems to reverse the natural flow of chaos, like a shattered glass reassembling itself. Some physicists argue this makes them impossible, while others suggest they might exist only in the most extreme conditions, like the first moments of the universe or in the depths of a quantum foam. There's even a wild hypothesis that white holes could be hiding in plain sight, masquerading as pulsars or other high-energy objects we've already catalogued without realizing their true nature. The search for white holes isn't just about ticking a box in relativity's playbook. It's a probe into the deepest questions of existence. Is the universe a one-way street toward entropy, or does it have a reset button? Are black holes truly the end, or just a chapter in a larger story? For now, white holes remain ghosts in the equation's shadows of possibility that challenge our understanding of time, causality, and the very fabric of reality. And perhaps that's their greatest gift, not as answers but as invitations to keep questioning, to keep imagining the universe not as it is, but as it could be. The vacuum of space isn't empty, it's a seething quantum foam, alive with particles flickering in and out of existence so fast we can never catch them. According to quantum field theory, every cubic centimeter of this so-called empty space should crackle with unimaginable energy, a roiling sea of virtual particles borrowing energy from the future to briefly dance in the present. When physicists calculate how much energy this quantum frenzy should contribute to the cosmos, the numbers are staggering, 10 to the power of 112 joules per cubic meter. That's enough to rip space-time apart instantly. Yet when we measure the actual energy density of the vacuum, the cosmological constant, it's almost zero. Not just a little off, but a factor of 10 to the power of 120 times smaller. It's like predicting a tsunami and finding barely a ripple. This isn't just a rounding error. It's the most embarrassing mismatch between theory and observation in the history of science, known as the Vacuum Catastrophe. How can our best theories be so spectacularly wrong? One possibility cuts to the core of quantum mechanics itself. The equations we use to calculate vacuum energy treat particles as point-like objects with no size, which leads to infinite energies that must be renormalized, a mathematical trick to sweep the absurdities under the rug. But what if this isn't just a technical fix? What if it's a clue that spacetime has a fundamental graininess, a smallest possible scale where quantum jitters smooth out? Theories like loop quantum gravity suggest that below the Planck length, a distance so tiny it makes an atom look vast, the concept of smooth space breaks down entirely. In this view, the vacuum's energy might cancel itself out in ways we can't yet model, like waves crashing together to leave a calm surface. Then there's the anthropic angle. If the vacuum energy were even slightly stronger, galaxies would never have formed, slightly weaker, and the universe would have collapsed long ago. Our existence hinges on this razor-thin balance, leading some to propose that we live in one bubble of a multiverse, where countless universes have different vacuum energies, and we, of course, find ourselves in the rare one where life is possible. It's a controversial explanation, criticized as unfalsifiable, but it underscores how deeply weird this problem is. The vacuum catastrophe isn't just about numbers, it's about whether our universe is fine-tuned, and if so, by what or whom. The most radical solutions rewrite physics entirely. Some theories posit that dark energy, the force accelerating cosmic expansion, isn't constant but evolves over time, dynamically adjusting to cancel out the quantum vacuum's excess. Others suggest gravity behaves differently at cosmic scales, with extra dimensions or modified equations masking the true energy density. String theory offers a kaleidoscope of possibilities, with its landscape of 10 to the 500 possible vacuum states, one of which might accidentally align with our observations. But until we find experimental evidence, these remain beautiful speculations. What makes the vacuum catastrophe so thrilling isn't the failure, it's the opportunity. Like a crack in a dam, it hints at pressures beyond our current understanding, forces that might reshape physics once they break through. Every experiment hunting for quantum gravity, from tabletop tests of spacetime foam to observations of distant supernova, is probing this mystery. The vacuum isn't just empty space, it's the stage where the next revolution in physics will unfold, waiting for us to listen closely enough to hear its whispers. In the vast, swirling chaos of the cosmos, where particles dance endlessly through eternity, there's a thought so unsettling it could unravel our very sense of reality. Imagine for a moment that your consciousness, your memories, your sense of self isn't the product of billions of years of evolution, but a fleeting accident. A single, self-aware brain, spontaneously assembled from random quantum fluctuations, flickering into existence just long enough to wonder, am I real? This is the Boltzmann brain paradox, a mind-bending consequence of thermodynamics that forces us to question whether we're more than cosmic static in an infinite universe. The idea springs from Ludwig Boltzmann, the 19th century physicist who uncovered the deep link between entropy and the arrow of time. In an infinitely old universe, he reasoned, even the most improbable events must eventually occur. Given enough time, a room full of monkeys typing randomly would produce Shakespeare, and given enough space-time, atoms jostling in the void could, by sheer chance, arrange themselves into a fully formed, conscious mind. Not attached to a body, not born of stardust but conjured from chaos, complete with false memories of a life that never happened. The odds are astronomically low, but in an endless cosmos, impossible loses its meaning. Here's where it gets even stranger. If Boltzmann brains are possible, they're statistically inevitable and infinitely more likely than the orderly, continuous existence we assume we're experiencing. Think about it. The universe manufacturing one self-aware brain through randomness requires far less energy and organization than crafting an entire species across billions of years. So why do we perceive ourselves as the latter? Either we're the miraculous winners of an inconceivably unlikely lottery, or we're momentary glitches in the void, destined to dissolve back into disorder before we can even finish this thought. Scientists recoil from this conclusion, not just because it's existentially horrifying, but because it undermines the foundation of empirical knowledge. If our minds could be Boltzmann brains, how could we trust any observation or memory? The laws of physics we've painstakingly deduced might be nothing more than elaborate hallucinations. To escape this nightmare, cosmologists propose solutions. Perhaps the universe isn't infinitely old, cutting off the time available for such flukes. Or maybe there's an as yet unknown law of physics that prevents conscious entities from forming spontaneously, a cosmic safeguard against existential dread. Yet the Boltzmann brain isn't just a puzzle, it's a mirror. However unlikely, its possibility forces us to confront the fragility of our assumptions about reality. Every time we look up at the stars, we're not just observers of the cosmos, but participants in a mystery far deeper than we usually dare to ponder. Whether we're stardust or statistical noise, the question lingers. In an infinite universe, what does it even mean to be real? And if the answer is uncertain, perhaps the real revelation isn't about the cosmos, but about the extraordinary fact that we're here to ask the question at all. From the fiery dawn of the Big Bang to the eerie stillness of the Boötes Void, these 29 cosmic tales have taken us on a journey where each revelation unravels new layers of mystery. The universe isn't just a static backdrop, it's a living, breathing narrative, constantly rewriting its own rules in ways that both humble and astonish us. Think about the threads we've followed. Dark matter's invisible scaffolding, the rebellious galaxies defying gravity, the diamond worlds glittering in the void. Each discovery isn't an endpoint, but a doorway, a signpost pointing toward questions we haven't even learned to ask yet. What makes these stories so compelling isn't just their scale or strangeness, it's the way they redefine our place in the cosmos. We're not passive spectators watching from the sidelines. With every telescope pointed skyward, every equation scribbled on a chalkboard, we're active participants in the greatest detective story of all time. The clues are etched in starlight, hidden in gravitational waves, encoded in the faint whispers of particles, and the most thrilling part, the case is far from closed. For every mystery we've touched on, from the wow signals cryptic burst to the phantom pull of Planet 9, there are countless others waiting in the darkness, just beyond the edge of our understanding. So as we wrap up this journey, let's not think of it as an ending but an invitation. The universe has spent billions of years crafting these enigmas, and they're not going anywhere. Whether it's the haunting possibility of Boltzmann brains or the cosmic tightrope walk of vacuum energy, these aren't just intellectual exercises, they're reminders that wonder is woven into the fabric of reality itself. Now it's your turn. Which of these cosmic narratives resonated most deeply? Was it the time crystals defying entropy or the Great Attractor's unseen pull? Drop your thoughts in the comments below, because in the grand conversation about the cosmos, every perspective adds a new dimension. Before you go, make sure to hit subscribe and ring that notification bell. Our next adventure into the unknown is always just around the corner, whether we're diving into the quantum foam or chasing the echoes of colliding universes. Until then, remember, the night sky isn't just a canvas of stars, it's a mirror reflecting our endless curiosity. Keep looking up, stay curious, and never stop questioning. After all, the next great cosmic revelation might be hiding in plain sight, waiting for someone like you to connect the dots.